Today we're going to be talking about negative feedback amplifier circuit. And we are going to start by taking a look at what conditions would make an amplifier circuit behave like an ideal circuit. Okay. Excuse me. So ideal amplifiers. So here in the middle of my screen, I'm just going to have our practical amplifier, single-ended input model, and then just apply the results of our analysis to an op amp. So we have Vn of t here. Over on this side, we have our open loop voltage gain times input voltage. Here we have our output resistance. So this portion of the circuit, again, represents the amplifier stage. On the source side of the circuit, we have some practical voltage source, RS, in series with Vs of t. And over here on the load side, we have our load resistance RL, across which we measure some load voltage VL of t. So here is source, amplifier, and the load. And this is what we came up with for the behavior of amplifier circuits way back on our second day of class when we first started talking about these things. Okay. So let's talk about what our ideal behavior for this circuit would be. Okay. The ideal behavior for this circuit would be that VL, the voltage drop that's showing up across our load, would simply be the scaled version of Vs, because that is the ultimate goal of the amplifier. We apply some signal and we want to see a scaled version of that signal at the output of our system. Right? So ideally, I believe we mentioned this previously, VL of t will simply be AV, some amount of voltage gain, times our source or signal voltage, Vs. So what we are going to figure out is what values of R in and R out will make that happen. Okay. So let's start with the input side of things here. Okay. So if we want Vs to equal VL, actually we can, I'm spitballing here. I'm thinking about us doing this in a slightly different way here. Let's think about this mathematically instead of conceptually like what I was about to do, right? I can write a voltage divider equation for this left-hand side, right? And I could see that Vn is going to be Vs of t times Rn over Rs plus Rn. And I can also write a voltage divider equation for the right-hand side of my circuit, right? Where VL of t is going to be AVOL times VN times RL over R out plus RL. And now I'm going to smash these equations together because that's going to give me VL in terms of VS. Right? So if I put these two results together, I could say that VL of T is going to equal to AVOL, our voltage gain, times VN, where VN is VS of T times RN over RS plus RN times RL over R out plus RL. And what I want to have happen is for these two expressions to be literally identical. So in the ideal case, VL is just a scaled version of VS, scaled by some gain. So effectively what I'm saying here then is that I want this coefficient Rn over Rs plus Rn to look like 1. And I want this coefficient RL over R out plus RL to look like 1. So what value of Rn makes this part look like 1? How large? Infinitely large. Absolutely right. So for the ideal case, I'll put this over here. Rn is effectively an open circuit. We can see that in our practical op amps that we've been dealing with input resistances on the order of mega ohms or larger. So that's generally speaking what these have been designed to do. But excuse me, if we look at this right-hand expression, RL over R out plus RL, how do we make this look like 1? What value of RS, or excuse me, what value of R out makes that happen? What's the smallest number? 0. Absolutely right. We want R out to effectively be a short circuit, which is why we've been seeing that the output resistance of our op amps is typically very small, on the order of single-digit ohms and all of that kind of stuff. Okay. So these are the parameters for the input resistance and the output resistance of an ideal amplifier. It's beyond the scope of this class to explain what I'm about to write down, but the ideal version of the open loop voltage gain is infinity as well. Okay. So just as a very brief thing, we're going to talk about this in much greater detail when you guys get into your electronics classes later on, when you're designing actual amplifier circuits from the ground up. One of the consequences of having an infinitely large open loop voltage gain is that when you apply negative feedback, the closed loop gain will be dependent only on the elements that you put in your feedback loop, which is exactly what we saw when we were looking at negative feedback amplifiers, right? So if we had an inverting amplifier, the closed loop gain was negative R2 over R1, or negative your feedback resistor over R1. It had nothing to do with the open loop voltage gain of the actual amplifier. It was established entirely by the feedback network. That is a consequence of having extremely large open loop gains, which most op amps have, okay? We'll talk about mathematically why that's important once we really dig into feedback systems in a later class, okay? So these three parameters are what we are assuming when we're dealing with an ideal op amp, okay? So now let's go back a step and let's analyze a negative feedback circuit with a practical op amp model and see how close we get to what we would have with an ideal op amp model, okay? So here is a simple negative feedback amplifier. Feed. We are going to have our op amp here. I have put the non-inverting input terminal on bottom. Here's VCC minus. Here's VCC plus. I'm going to have some resistance in my feedback loop. Let's call this RF. Here is my output resistance, excuse me, my output voltage terminal. On this side, I'm going to have some resistance R1. And then this is the input voltage to my system. So I'm going to call this VS, my signal voltage. And for this example, let's say that R1 is equal to 5 kiloohms. R2 is equal to 10 kiloohms. Our signal voltage is equal to 1 volt. And then our practical op amp parameters will be Rn will be equal to 1 mega ohm. R2, excuse me, R out will be equal to 100 ohms. Pretty large for an output resistance, but we'll see that that's okay. And our open loop voltage gain will be 10 to the 5 volts per volt. So we're going to analyze this circuit using the practical op amp model. We're going to determine the following quantities. So I want us to figure out A, the output voltage of our system, B, the closed loop voltage gain of our system, C, the input resistance seen by our input signal. So effectively, the resistance that we see looking in there, right? So specifically, we're just going to apply Thevenin's theorem and say that this voltage divided by whatever current is flowing in is the resistance seen by that voltage source. I also want to figure out D, what the output resistance is. So that's going to be the resistance seen looking into the output terminal. And E, what our differential voltage is. And honestly, we're probably going to solve for E before we get to those input and output resistances. But this is how I have it ordered in my notes, so that's what I wrote down. All right, so the most challenging thing about this particular circuit is going to be redrawing this thing using the practical op-amp model. Everything else is literally circuits one level of analysis. We're just going to do nodal because that's what you do when you're dealing with op-amps. Okay. So I'm going to start by drawing my practical op-amp model. Here's my input resistance. I am going to do something slightly different here than I've done previously. I'm going to call this terminal down here my non-inverting input terminal, and this terminal up here my inverting input terminal, just to make the feedback loop easier to draw. Okay, it's not going to change the analysis at all or anything else, but this terminal down here is going to be V plus. This terminal up here is V minus, which makes our differential voltage VD have this particular polarity. Then I have my open loop voltage gain times VD. Over here, I have my output resistance R out. Across these terminals, I'm measuring my output voltage. And this is my reference. So now let's connect things. Okay. My non-inverting input terminal is tied directly to ground. So I'm just going to tie it directly to ground. My inverting input terminal sees a resistance R1 in series with my signal voltage Vs. Like so. And let me scroll up so you can see it. I also have a feedback resistor connected between my inverting input terminal and my output terminal. So here is, oh, I called it R2 up here. I should call it RF, so the notation is the same in both. My apologies. There we go. So this is our circuit represented by the practical op-amp model. And we are going to apply Kirchhoff's current law at the inverting input terminal and at the output terminal in order to solve for some quantities here. Okay. So for my KCL equation at my inverting input terminal, I'm going to be adding this current plus this current plus this current together. And so I'm going to have V minus Vs over R1 plus V minus 0, since V plus is 0, over Rn plus V minus V out over Rf is equal to 0. So there's my KCL equation at my inverting input terminal. Just for the sake of argument here, since I want us to solve this thing, I'm going to rewrite this using the numbers that we have. All right. So that's going to look like V minus 1 volt over 5 kiloohms plus V minus over 1 mega ohm plus V minus minus V out over 10 kilo ohm is equal to 0, but we can throw this in our calculator in a moment. Now I'm going to apply Kirchhoff's current law at my output node. So I'm just going to add those two currents together that I designated in purple. So my current flowing to the left is going to be V out minus AVOL times VD over R out. So V out minus AVOL. I'm going to put something here, even divided by R out. What is VD in this case? Exactly right. 0 minus V minus or negative V minus. So I'm going to put a V minus right here. And I'm going to change that sign to positive, and that takes care of my algebra. I also have the current flowing up. So that's going to be V out minus V minus over RF. Is equal to 0. And I'm going to rewrite this guy using numbers as well. So V out plus 10 to the 5 times V minus over 100 ohms plus V out minus V minus over 10 kilo ohms is equal to 0. We now have two equations and two unknowns, so we can solve. All right. So if we solve 1 and 2 simultaneously, what we will get is that V minus is equal to 20.199 microvolts. And V out will be equal to negative 1.9999392 volts. So before we get into the weeds of doing math and stuff like that, let's think about a couple of things here real quick. Okay. V minus is 20.199 microvolts. V plus is 0 volts. So our differential voltage here is just going to be negative this number. What's interesting about this number? Anybody have any thoughts? Really small, really small. You're absolutely right. You might call it 0 or something close to that, right? What do we know from circuits 1 about the potential difference between the input terminals on an ideal op-amp? It's 0. So in a practical op-amp, it's not 0, but it's real close, right? That's because this input resistance is so large and this voltage gain is so high. Okay, so we're seeing things start to shape up here. All right. What would we expect the voltage gain of this system to be from an ideal op-amp perspective? It's okay if you don't remember it, but for this particular amplifier, this is what's called an inverting amplifier. The voltage gain should be given by negative the feedback resistance divided by the resistor R1, which in this case would be negative 10 over 5 or negative 2. And we see that we're getting an output voltage of negative 1.9999 and change for an input signal of positive 1 volts. So our gain is effectively negative 2. So everything indicates here thus far that we're behaving pretty close to the ideal case, even though we're using finite values. Okay. All right, so just for the sake of argument here, A was finding V out. We found that negative 1.9999392 volts. B was finding our closed loop voltage gain, which is going to be the ratio of V out to Vs. So that is negative 1.9999392 volts per volt. E was finding Vd, which is V plus minus V minus, or negative 20.199 microvolts. Everything that we've seen here agrees with what we would expect for an ideal case, right? So this input resistance and this output resistance thing, we're going to calculate them because I want you guys to understand how to calculate them and all of that kind of good stuff. It's not going to be a big part of things in this particular class, but it is something that we're going to do over and over and over again once we get into our electronics classes and all that kind of stuff. So treat that more or less like I'm just introducing you to a concept than it having any real practical purpose here, okay? We are going to see a couple of things, but the input resistance here is going to be wonky-ish from what you would expect. It's not going to be infinity, effectively. And the reason it's not going to be infinity is because we're looking in through a resistor into infinity instead of looking directly into infinity. Anyway. All right, so let's figure out how we're going to calculate this input resistance, right? So I'm calling this resistance that we're trying to find here the resistance seen looking into that leg of that resistor R1, okay? So effectively, if I had a voltage source here, and then I knew how to calculate the current flowing into here, this lowercase rn would simply be the ratio of this voltage to that current, right? Well, luckily for us, you can easily figure out what that current is because we know what the voltage at this node is, right? So for C, we are going to have Rn will be equal to that voltage, which was 1 volt. Actually, let me write this out symbolically and then we'll throw numbers in so it's not too confusing. This is going to be Vs minus V minus divided by R1, which is the same thing as, that doesn't look like a 1, that looks like an L, my apologies, which is the same thing as Vs times R1 over Vs minus V minus. So putting in numbers, 1 volt times 5 kiloohms divided by 1 volt minus 20.199 microvolts is going to come out to be 5,000.100997 ohms. About 5 kiloohms, or exactly the resistor that we put in front of the input path. To calculate our output resistance, let's look at things we have here. So to calculate our output resistance, we are going to apply a test source. Actually, that's one way to do it. One way to do it would be to apply a test source to the output terminals of our dead network and then find the Thevenin resistance. But we could also use the find the Thevenin resistance by determining the open circuit voltage and the short circuit current there, right? I'm going to use that second method because we already figured out what the open circuit voltage was, because this is an open circuit. So V out that we calculated at the beginning is our open circuit voltage, or our Thevenin voltage for this system measured between our output terminals. Now we'll just need to figure out what the current is through sorting out those terminals, right? So let's do this in pink here. I'm just going to modify this drawing here and make a note that this is the Norton current that we're trying to find. Okay. How is this going to change the KCL equations that we've already written? What's V out now? It's 0 because we shorted it out. So we're forcing it to be V out, right? So anywhere we have V out is now equal to 0, which means we really only have one unknown voltage in this whole thing, right? So if we look at this first equation with V out now equal to 0, we can solve for this quantity V minus. Again, it's going to be a different number. And then knowing that, we'll have this current flowing in plus this current flowing in will be equal to our Norton current. Right? So I'm going to solve this equation again. Let's put D down here. So I'm just looking at this guy right here. So V minus minus 1 volt over 5 kiloohms plus V minus over 1 mega ohm plus V minus over 10 kiloohms is equal to 0. We can solve that and find that V minus is 0.66445 volts. Using this value of V minus, now we're going to write a KCL equation here. So we're going to say I Norton is equal to this current flowing in, so that's V minus over RF. And then we have this current flowing in, which is AVOL times VD, or AVOL times negative V minus divided by RF. Everybody okay with that? Okay. That looks like a terrible VOL. So that's going to look like 0.66445 volts over 10 kiloohms minus 10 to the 5 times 0.66445 volts divided by 100 ohms, which looks like negative 664.45176 amps. I want to be real clear here. If we shorted out the output terminals of our op amps, there is no way in hell it would carry 650 amps of current. It would fry well before that. This is a theoretical construct that we're using to determine something. Hannah, you were raising your hand. Open loop gain, closed loop gain. So the open loop gain is how this voltage generates this voltage, right? So that's the relationship between the output side of this thing and the input side of this, right? So the output voltage present here is the open loop gain times the differential voltage. Our closed loop gain is the voltage measured across our output terminals divided by the input signal that we're applying outside of the closed loop, right? So did that clarify things? Okay. Our Thevenin voltage, just to repeat things here, was negative 1.9999392 volts, which we got by determining V out for our first condition where the output terminals were open circuited. And so lowercase r out is just the Thevenin resistance seen at the output terminals, VTH over I Norton, negative 1.9999392 volts over negative 664.45176 amps comes out to be 3.0085 milliohms, real close to zero, which is pretty much what we would expect. In fact, at some point, I'm just going to have to update this to be a non-inverting amplifier, and then you would see that the input resistance would be really close to infinity or much larger than Rn, but I keep forgetting about it until I get to this point and realize I could have done this better. But anyway, so we're seeing largely that things behave much like we would have if we had used simply the ideal op amp model, okay? So unless I specifically tell you to use the practical op amp model for a negative feedback circuit, you can just use the ideal op amp model and get approximately the same result. As a matter of fact, if you look at homework set number 5, maybe 4, what are we on now at this point? 4 now. So if this is our 4th class meeting, then this should be homework set number 4, I think. This is our 5th class meeting. Yeah, so homework set number 5. I literally have you work the problems using the practical op amp model, then have you work the problems using the ideal op amp model, and then calculate the amount of error introduced by using the ideal model. And you'll see that it's a trivial amount of error, because for all intents and purposes, anytime we have a negative feedback op amp system, it's effectively going to behave like an ideal amplifier. Even if our voltage gain is only 1,000 or so, instead of hundreds of thousands or millions. Even if our input resistance is only hundreds, 10,000 ohms or something like that, instead of millions of ohms or more. Even if our output resistance is hundreds, if not thousands of ohms, instead of really close to zero, like we would expect for an ideal case. We have to really screw things up in a negative feedback configuration to not have it behave like an ideal op amp, plus or minus 10%. All right, so that's a good stopping point for today. What we are going to do on Monday's class is we're going to go over those negative feedback op amp topologies that I talked about way back in circuits 1. Literally the exact same thing. The expectation now that you guys are circuit to students is that you'll be able to recognize them and then use those relationships to analyze circuits, as opposed to using that three-step process of finding the voltage present at the non-inverting input terminal, finding the voltage present at the inverting input terminal, and then applying KCL to figure out V out. Once we get through those, then we're going to talk about cascading op amps together to make larger amplifier circuits to do things. All righty, see you guys next Monday. Have a good weekend. Tell you guys the same thing I told my Circuits 1 students. Have a happy and safe St. Patrick's Day. Try not to be too belligerent and try not to get arrested.